Afternoon. I'm Diego Bellan with the Department of Electronics, Information and Bioengineering of the Politecnico di Milano, Italy. And my speech today is about the Clarke circuit analysis for space vector ellipse characterization of phase-to-ground faults in three-phase radial systems. As you certainly know, power quality is a major issue in modern power systems because of the increasing complexity of the system and the presence of many nonlinear components. In recent years, a new methodology has been introduced in power quality analysis. And this methodology is based on the analysis on the space vector trajectory on the complex plane. This approach can help in disturbance detection and classification. And in particular, it is useful in the analysis of voltage sags due to fault conditions. In fact, while under ideal condition, the space vector trajectory is circular, under fault conditions, the voltage space vector traces an elliptical trajectory on the complex plane. Moreover, the inclination angle of the ellipse allows the classification of the type of fault. This figure shows the typical inclination angles of the space vector ellipse for different kinds of faults. For example, you can see here a single fault on phase A results in ellipse inclination around 90 degrees. Or a double phase fault involving phases B and C shows an inclination angle around 0 degrees, and so on. In the existing literature, the problem has been approached by solving three-phase faulted circuits through conventional circuit analysis in the natural ABC domain, for voltages and currents, of course. Then the Clarke transformation was used to transform the ABC variables into the space vector components in the complex plane. Since such approach does not operate directly on the space vector components, it cannot provide direct insight into the relationship between the fault and the space vector components. This is the so-called alpha and beta components. In other words, the conventional approach does not provide any equivalent circuit in the Clarke transformed variables, that is the space vector variables. In this paper, a circuit methodology is introduced based directly on the Clarke transformed variables. These are the components of the space vector. Equivalent circuits are derived directly in the Clarke variables, alpha, beta, and 0. And this allows a straightforward determination of the space vector components, alpha and beta. And finally, it allows to establish a direct link between the derived equivalent circuits and the space vector properties. We recall now that the Clarke transformation is a linear transformation between the ABC phase variable, for example, the phase voltages, ABC, and the new Clarke variables, alpha, beta, and 0. This transformation is very useful because it results in the diagonalization of the matrix of basic symmetrical three-phase components, such as three-phase inductors. The space vector is defined here as a time domain complex valued function whose real part is given by the alpha component and the imaginary part is the beta component of the transformed variables. It can be shown that under sinusoidal conditions, the space vector is given by the sum of two phasors rotating in the opposite direction. That is the positive sequence phasor and the negative sequence phasor. Under ideal conditions, however, the negative sequence phasor is 0. Thus, the space vector has a circular trajectory on the complex plane. Under faulted conditions, however, the negative sequence phasor is different from 0, and therefore the space vector has an elliptical trajectory. The aim of obtaining equivalent circuits in the Clarke domain, we need to understand how symmetrical connections are transformed. The first case is the star connection with non-accessible center. In this case, the three voltages are equal, of course, and the sum of three currents is 0. Therefore, by using the Clarke transformation, we obtain that the alpha and beta components of the voltage are 0, and the 0 component of the current is 0. It means that this connection is equivalent to a short circuit for the beta and alpha components, which is for the space vector, and an open circuit for the 0 component. The second interesting connection is the star connection with accessible center. In this case, the sum of three currents is not 0, of course, but it is equal to the current in the single phase network here, single phase network, connected to the three-phase port. By using the Clarke transformation, we obtain the same results for the alpha and beta voltages as before. That is, the connection is still a short circuit for the space vectors. But in this case, for the 0 component, we obtain that the three-phase network is connected to the single-phase network through an ideal transformer with turn ratio equal to the square root of 3, this one. Our objective, however, is studying asymmetrical faults in the Clarke domain. Notice that an asymmetrical fault can be modeled as a three-phase switch where only one or two switches are operated. Since the operation is asymmetrical, the methodology outlined above before cannot be used in a straightforward way. Therefore, we introduce a new methodology based on the well-known Thevenin theorem. To this aim, the asymmetrical three-phase switch is detached. Then the Thevenin equivalents of the remaining symmetrical circuits are considered. Then the constraints introduced by asymmetrical faults are taken into account in the Clarke domain through a proper interconnection of the Thevenin equivalents. Let's consider the case of a single phase fault. By considering a faulted phase A, the line A, the corresponding constraints are given by, of course, VA equal to 0. It means that this switch is closed. So VA is equal to 0, and the two currents, IB and IC, are 0. By using the Clarke transformation, the constraints become the following, these ones. That is a relationship between the alpha and 0 components of voltages and currents through the coefficient square root of 2 and a 0 value for the beta component of the current. It means that in order to study this fault, the alpha and 0 Thevenin equivalents must be interconnected through an ideal transformer, whereas the beta Thevenin equivalent must remain open. This result is depicted in these two figures. In the first figure, you see the interconnection between the alpha and 0 Thevenin equivalents through the ideal transformer defined before, whereas the beta Thevenin equivalent is open because the beta current must be 0. The following example is used to show the application of the methodology outlined before. Let's consider a radial three-phase system with an equivalent generator here at the point of common coupling PCC, a ground impedance, a load impedance, of course, a fault impedance, and a line impedance. Notice that the location of the fault is defined by the variable x. Okay. According to the general circuit methodology derived before, the single phase fault can be analyzed by studying the two circuits shown here. The first circuit is given by the interconnection of the alpha Thevenin equivalent and the 0 Thevenin equivalent. The two equivalents are interconnected through an ideal transformer with turn ratio 1 over the square root of 2. From the proposed circuit, the evaluation of the alpha component of the voltage is very simple, of course. It's trivial. The second circuit is the beta circuit in open conditions. that is with zero current. Notice that from this circuit, we can easily derive that the beta component of the voltage is not affected by the fault. This result is possible only through the approach proposed in this paper, where the equivalent circuits are derived directly in the Clarke domain. According to the general scheme already shown at the beginning of my presentation, for the single phase fault here, with faulted phase A, we should obtain for the voltage space vector an elliptical shape with inclination angle around 90 degrees. Actually, this is the trajectory of the voltage space vector on the complex plane. Different ellipses are shown for different locations of the fault. That is, you see the variable x is ranging from 0.1 to 1. Notice that according to the equivalent circuits obtained before, the beta component, that is the imaginary part on the vertical axis, is not affected by the fault. Only the alpha component, that is the real part on the horizontal axis, is affected by the fault. These two figures compare the cases of two lines with different length, 5 kilometers and 15 kilometers on the right. Notice that a longer line results in a larger spread of the elliptical shapes. These two figures show the effect of ground and fault impedances. By introducing ground and fault impedances on the right side, we can notice a slight change in the ellipse inclination and a smaller spread of the curves. Finally, we can notice that if the faulted phase is B or C instead of A, we obtain a simple rotation by plus or minus 120 degrees of the ellipse, like in this figure. Some concluding remarks. We have shown that the proposed approach allows a straightforward interpretation of the properties of the space vector ellipse used to detect and classify an asymmetrical fault. The proposed approach has been derived in detail for the case of a single phase to ground fault. Future work will be devoted to extend, of course, the analysis to double phase faults and to investigate the impact of system impedance. Thank you for your attention.